Hello guys, great morning. So we will be discussing today deformations and strains as a continuation for our stress concepts. So we know for a fact that the resulting consequence of the application of stress is to allow the body to deform. And this deformation can be converted into a unit deformation, which is known as strain. So let's consider now a spatial system y1, y2, y3, which is right-handed in terms of the position and arrangement of the axis. And considering a continuous body, okay, which is allowed to move and deform. So the spatial description or position of such particles within the body may be described in terms of the original or undeformed state, and the final or deformed state of the body. So let us try to consider now a point P, particle point, inside the body being displaced at a distance u, okay? So P becomes P prime, and the distances from the origin is given in terms of the big X here and a small x there, okay, such that the big X is the spatial description in terms of the original position of the body, while the small letter x is the final description in terms of the position of the body at time t. And therefore P and P prime becomes a function of big letter X or capital X, 0 at initial time t, and small letter x, or sorry, P prime is a function of small letter x at a certain time t. So this description is actually a function of position and time, wherein the 0 value there simply connotes that your time t there is actually equal to 0. So for the description of the particle position in the continuous body or continuum, we call this the configuration. We will be using The description in terms of Lagrangian, which describes the initial, the material, and the undeformed configuration, whereas the Eulerian is described by the instantaneous, spatial, and deformed configuration. So this means that when we talk of the Lagrangian description, it's named after Lagrange, and when we talk of Eulerian description, which is named after Euler, we simply refer to the original position and the final position respectively. Note that the particle P is a small volumetric element in the continuum defined by the position vector R, which is this one. Okay, so to understand better what we're talking about here in this particular system, so we consider a rectangular body, say ABC, which is allowed to deform in terms of lateral displacement, assuming that the bottom part AD is fixed, and upon application of a load, what happens is that point B goes to point B prime there, and point C goes to point C prime. Hence, for very small deformation, we assume that AB and AB prime subtend an angle of omega, which is actually an angular displacement that describes the shear strain of the body ABCD in the original state and AB prime DC prime in the final state, or simply the Lagrangian state and the Eulerian state respectively. So take note that when we're talking of the original state or description or the Lagrangian description, we refer to the mathematical function small x is equal to the function of big X. Okay, so this can actually be abbreviated by simply using the index I in this regard. Okay, so this is a vectorial notation, while this is more of a tensorial notation or an indicial notation. So if you want to take a look at point P, the particle movement from P to P prime, since this body is fixed at the bottom AD, then the movement of the particle P will be parallel to the x1 axis such that your x1 displacement is simply defined by the original, okay, the original position capital X1 plus the original position capital X2 multiplied by the angular deformation or displacement and time t. Okay, so we consider now that omega changes, varies as the time moves from an initial value 0 to an instantaneous value t. Okay, so this is simply uh, a formula, okay, that gives this displacement here equivalent to whatever height is this, which is described by x2, capital X2, and then the tangent of this angle omega will give you the movement pp prime in the horizontal direction. Since this is a very small angle, then the tangent of omega is simply equivalent to the angle itself. Hence, this displacement, as described previously by capital X1 here, is added a value which is this one here. Okay, so in the vertical description, x2 does not change. Therefore, x2 is simply equal to x2 capital, and also on the direction perpendicular to the plane x1, x2, then x3 does not change. Hence, x3 is simply equal to capital X3. And if you want to take the inverse description from Eulerian to Lagrangian, we simply take note of this value. Okay, so I'd like to apologize that there's an error here on the copy and paste uh, error. So this must be capital X1 is equal to small x1 plus omega x2 t. Okay, so it's a simple uh, algebraic manipulation. Okay, so if I have here this equation, how do I solve for capital X1? I simply transpose this on the other side, so this becomes small x1, okay, minus omega capital X2, okay, multiplied by t. But x2 must be converted into an Eulerian description, therefore this becomes now x1 minus omega x1 times t. Okay, so this must be negative sign. And so is true with x2. Okay, so x2 is simply equal to small x2, and x3 is simply equal to small x3. Okay, take note that for a Lagrangian description, x is to the capital X of functions, okay, and here we have capital X is a function of small x. Okay, so that's how to do it when we solve arguments in terms of the Lagrangian and the Eulerian description. Again, the Lagrangian description may be termed as initial, material, or undeformed, or original. No? and the Eulerian description may be termed instantaneous, spatial, deformed, or final configuration. So let's go back to some matrix algebra concepts here, wherein a Jacobian is defined as the partial derivative of the Lagrangian description with respect to the Eulerian description, or simply the Jacobian is the determinant of the partial derivative of small xi with that of the capital Xi. And if we will take a look at the expanded form of this initial uh, uh, expression, so we can come up with a matrix, okay, in terms of this. Okay, so I think there is just some errors here. This must be uh, no. Since this is a determinant, this is consistent, must be consistent. Some, yes. Okay, so this is correct, no? This must be a scalar value class. The J must be a scalar value. And this is a summation xi, because we're doing a determinant operation here. In this case, okay, so we're doing a determinant, so this plus this minus, okay, this minus this, and this. Okay, so it's a summation. Repeated index means that this is the sum of the diagonals formed using a determinant operator. Therefore, this is a scalar. So from the preceding example, we have this assured Lagrangian description. Okay, so don't be confused about this. And if we take the partial derivative of x1 with respect to x1, okay, we're now taking xi, which is x1, with respect to x1 capital. So this is just a derivative of a variable with respect to the same variable, it's 1. So all of this will be 1, 1, 1, and this will of course be omega t. So there's a missing variable there, which is t. So again, I'm sorry for the error. Okay, so the partial derivative of omega x2t with respect to x1 is simply omega t. Okay, so if we take a look at this one here, okay, the partial derivative of omega x2 t with respect to x2 rather is simply equal to this. And of course, since these are all zero, so this must always also be 0. And taking the determinant of this Lagrangian derivatives, and we get here a value equivalent to positive 1, and therefore in matrix linear algebra, for an inverse function to exist, or for a set of equations to have a solution, then one way of checking is to get the Jacobian of the matrix, and this must not vanish in order for the set of equations to be non-singular. So non-singularity simply means that there is a solution, no, to the set of equations. And there's also an inverse function, because there can be no solution if there is no inverse function. So from the above illustration, we now create some simpler expression in terms of the material deformation gradient and the spatial deformation gradient, or simply this is again the Lagrangian deformation gradient and the Eulerian deformation gradient. So this partial derivative with respect to of xi with respect to xj is simply f, and the partial derivative of capital Xi with respect to xj is simply h. Okay, so again, one correction here, class. This is not j, this must be I. So this is a Jacobian j, and these are not equal. Okay, so I just like to caution you, these are not the same. So when I ask somebody to type this for me, my students then thought that these are just the same. So this is different because this is actually a matrix, okay? Because ij has two free index, therefore this is 3 squared, 9 components. Okay, and so it's true with this one here. 3 squared, we have 9 components. While this is a Jacobian, which states that this is simply the determinant of the partial derivatives of xi with respect to xi. Okay? Okay. So we note that f and h are the inverse of each other. So they are just like saying if y is equal to x plus 1, then x is equal to y minus 1. So these two equations here are simply the inverse of each other. Okay, so f and h are just inverse. In terms of initial notation, we can say that fik dot hkj will now be equivalent to the Kronecker delta or the identity matrix, since these values here are the inverse of each other. Okay, so it's just like saying what is x times x to the negative 1, the inverse of each other, so this is 1. Okay, or simply x times 1 over x is equal to 1. So this must be property that must be satisfied. Or in terms of straightforward notation, f dot h is simply equal to 1, or vice versa. So now, if we let u be the displacement vector, we say that from the figure above, okay, so let's go back to this figure here. What is the vectorial okay expression that will yield the value of u if this is capital X and this is small x. So vectorially, okay, since this is now a a uh, a vector, it has a magnitude with a sign, then we can say that x, capital X is simply equivalent to small x minus u. Okay, so if capital X is small x minus u, then u is simply equal to small x minus capital X. And this is now our vectorial equation or expression for displacement field. You call this now a displacement field to represent a displacement vector that has a magnitude and a direction. So note ux and capital X are simply vectors. So if we take the partial derivative with respect to x, this material description, because we're taking it as a partial derivative with respect to x, remember our definition of Lagrangian is that the function is described with respect to the capital xi. So this is now a Lagrangian description or a material description. They're just the same. Okay, so ui now, partial of ui with respect to capital Xj is equal to partial of small xi to respect to capital Xj minus partial of capital Xi with that of with respect to capital Xj. So this becomes now what? What is this? This is simply a Kronecker delta. Okay? So remember that this is a function of position. A function of position, we will come up with a Kronecker delta, which is simply in terms of straightforward equation. So this is simply j, okay, as defined above here. Okay, so where's that? J and F, J and F. Okay, so this is F. What is your J? Okay, so this, okay, so this was not defined above. It was defined here below. Okay, so if we let J be this one, and we know that this is F as defined above here. Okay, so this is F, a little bit confusing. So this is F, and this is a Kronecker delta, which is simply in a straight equation equivalent to 1. So this is now our formula for the material displacement gradient. Take note, J here is not a Jacobian. So the J here is a cursive J. I just couldn't write a cursive J like this in MathCAD. So this is it's cursive J, and this is a bold, okay, letter J is known as the material displacement gradient, which is again a Lagrangian description. So similarly, if we take the partial derivative with respect to the small x, so it will just be changing in terms of this part here. This becomes small. So the number 1 or the Kronecker delta will fall on the first term here, and this becomes your h, okay, as defined here above. Okay, so this one here. And if we let k be this partial derivative of ui with respect to xj small, then simply k is equal to 1 minus h. So this is h. And you call this now what? So if j is the material displacement gradient, this is now spatial displacement gradient, or simply an Eulerian description. Okay, so because again, we take a look at our definitions here, Eulerian is a spatial, okay, while Lagrangian is a material description. So that's it for the introduction on deformation and strain. We will continue some more of the concept of determining and deformation tensors on the next video. Thank you very much for listening.